Hello everyone. In this video lecture I will explain to you the orthogonality of natural modes for the natural modes of vibrating beams. For that we need the equation of motion for vibrations in beams as well as the boundary condition for a specific example for which you have already derived the natural frequencies and corresponding natural modes. So in our case, I will stick to the example of the previous lecture of the simply supported beams. And let me state the expression for the natural frequencies, omega n. We found them to be n squared pi squared times the square root of EI divided by rho A L to the power 4. And we also derived the expression for the natural modes, Vn. They are some arbitrary scaling coefficient times the sine of n pi x divided by L. And there are infinitely many of them, so n is 1, 2, etc. So in this lecture, I'm going to demonstrate a couple of properties of mode shapes. This will hold in general, and we will need it for determining free and forced vibrations of the of beams. And in this process we will again see that we are able to mass normalize the modes. So basically we will decide on what we choose for this arbitrary scaling coefficient alpha. So let me pick now two sets of natural frequencies and modes, omega I Vi and omega j Vj. They satisfy the following equations. Let me see, we have a minus omega I squared rho A, and then we just have Vi plus EI times Vi fourth derivative, that is equal to 0. And similarly for some other natural frequency, omega j squared, and the corresponding mode Vj holds that they satisfy this equation. Vj 1, 2, 3, 4 equal to 0. Okay, let me now multiply the first equation by Vj, the second one by Vi, and I will integrate both along the entire length of the beam from 0 to L. So then we get minus omega I squared rho A integral from 0 to L Vj Vi dx plus EI times the integral from 0 to L Vj Vi 1, 2, 3, fourth derivative dx. This is equal to 0. And here very similar, minus omega j squared rho A integral from 0 to L Vi Vj dx plus EI times the integral of Vi Vj fourth derivative dx also equal to 0. So I will manipulate these equations such that the integrals are the same. For the mass term you see that that is already the case. For the stiffness that is not the case, because Vi and Vj might be distinct modes, and that means that Vj times the fourth derivative of Vi is not necessarily the same as Vi times the fourth derivative of Vj. So in order to fix that, we will use integration by parts. Let me just manipulate the first equation. So the integral of Vj Vi fourth derivative can be rewritten using integration by parts as Vj times Vi and then the third derivative at the boundaries 0 and L minus the integral from 0 to L of Vj first derivative times Vi third derivative dx. Now, if I would also do this for the integral in the right equation, you will get also a term that must be evaluated at boundaries, and an integral of vi first derivative, vj third. So after this, it is still not the same. And the way out is that this final integral must be integrated by parts once more. So that means that we write this as well. This first term is maintained, 1, 2, 3 at boundaries. And then we have minus vj first derivative, vi second derivative at the boundaries. Minus times minus becomes plus, and then we get the integral of vj second derivative, vi second derivative dx. So if I would do this for the equations on the right, the final integral will be the same, only the terms in between boundaries, the terms in between the square brackets will be different. But let's see, they must be evaluated at the boundaries. Let's have a look at the boundary conditions of our problem. We see that the displacement at 0 is 0 and also at L. So that means that all mode shapes, all these sine functions are 0 at 0 and L. So that means that this term here is 0 at 0 and L. Also, we see that the second derivative is 0 at 0 at L. And that means that this term is also 0. So again, we see that these terms at the boundary vanish. And that means that these two equations can be rewritten conveniently. So we get minus omega I squared rho a times the integral of vj vi dx plus ei times the integral of vj second derivative vi second derivative dx. And for this equation we get minus omega j squared rho a integral vi vj dx plus ei times the integral of vi second derivative vj second derivative dx. Oh, and these both equal 0, of course. So now you see that these integrals are all the same. So I can subtract the first equation from the second. In this way we obtain that omega I squared minus omega j squared times this integral of vi vj dx must be equal to 0. And that means that for I is not equal to j, we have to conclude that the integral from 0 to L vi vj dx must be 0, because omega I and omega j are distinct numbers. Then by back substitution of this result in any of these two equations, we also conclude that, that this was an integral from 0, that the integral from 0 to L of vi second derivative vj second derivative dx is 0. Now these are two very important relations, the orthogonality conditions are they called, that these modes are, if we take any two modes, let me first write down orthogonality conditions. So if we take any two modes and we multiply them and integrate, the result is 0. And if we take the second derivative of any two modes and integrate, the result is 0 as well. So it says that the modes and the second derivatives of the modes, that they are orthogonal with respect to distinct modes on the interval 0L. Now for I is j, of course omega I equals omega j, and that means that this integral can be any finite number. Then by rewriting the equation I marked with an arrow here, we conclude that ei times the integral of vi double prime squared dx divided by rho a times the integral of vi squared dx must be equal to omega I squared. And this is where we get this mass normalization from. Mass normalization. The idea is that we realize that the mode shapes still contain this arbitrary scaling, and we choose it such, we choose alpha such that this denominator equals 1, that rho a times the integral of vi squared dx equals 1, and as a consequence this means that ei times the integral of vi double prime squared dx will then equal omega I squared. So these are the orthogonality conditions. The procedure is fairly similar as what we've seen before, except for the case that we need to apply integration by parts twice. Let's now see how to choose alpha for this specific example of the simply supported beam. Okay, for that we look at this mass normalization and we conclude that, let's substitute this mode, so we get rho a alpha squared times the integral from 0 to L of sine squared of n pi x divided by L dx, and this must equal 1. So I will rewrite this by using that this sine squared of something can be written as a half minus a half cosine of 2 something. So if we do this, we get rho a alpha squared times the integral from 0 to L of a half minus a half cosine 2n pi x divided by L dx, and this equals 1. So if we carry out the integration, we get rho a alpha squared, and then we have a half x, and then we get minus, let me see, 2n pi in the denominator, so that becomes 4n pi. In the numerator we have L times the sine of 2n pi x divided by L. Evaluated at boundaries 0 and L, this must be equal to 1. So if we look at this sine term, we evaluate upper limit, the sine of 2n times pi, that's always 0. And evaluating the lower limit, the sine of 0 is 0, so this one drops. And for a half times x, only the upper limit produces something, so we have a half rho a L alpha squared is equal to 1, from which we conclude that alpha must be equal to 2 divided by rho a L. And hence the mass normalized mode shapes Vn equal square root of 2 rho a L times the sine of n pi x divided by L. So this is the value of alpha for which the modes are mass normalized. Alright, so that means now if we use this value of alpha and would now compute this integral, then indeed the result will be the expression for the natural frequencies of our specific problem squared. Okay, but I will leave that up to you as an exercise. So with this we have established the mass normalized modes and the orthogonality conditions. So I think we are fully prepared now for the free and forced vibration response analysis that we will do in the next lectures. I hope to see you there again. Thanks for watching.